Hey everyone, today I have prepared a bunch of facts about math, 101 to be exact, and I am going to tell them to you to help you relax today. This took a while to make, so I hope you enjoy. Also, if you want to listen to these episodes on Spotify, you can go subscribe to my Patreon. There are multiple other benefits, and it helps support the channel. But without a further ado, let's start at the very beginning with Fact 1. The oldest known mathematical object in the world is a baboon bone. It was found in the mountains between modern-day South Africa and the Democratic Republic of Congo in a place called the Lebombo. The bone is about 43,000 years old, and it has 29 notches carved into it in a clear, deliberate pattern. Nobody knows exactly what the person who carved it was counting. It might have been days, it might have been something else entirely, but those notches are organized. They were put there on purpose, and that right there is math. The oldest math we know of was a bone with scratches on it. That's where we start. And that leads us right into Fact 2. About 30,000 years ago, a wolf bone was found in what's now the Czech Republic, and it has 55 notches carved into it, arranged in groups of 5. That grouping matters. Grouping by 5 means the person doing the counting had figured out something subtle, that counting doesn't have to be one long chain of marks. You can chunk it, you can group it. That's called a tally system, and it's still the default way that humans keep score today. Look at any scorecard in any game played by children anywhere in the world, and there's a good chance you'll see groups of 5 scratches. 30,000 years later, we're still doing what whoever carved that wolf bone figured out. The reason we group in 5s, by the way, leads us directly to Fact 3. So, Fact 3. We almost certainly count in tens because we have 10 fingers. This seems obvious to the point of being boring, but follow the thread for a second because it has enormous consequences. Every culture that developed a number system independently, every single one, came up with either a base 10 system or a base 20 system, which would be finger counting plus toe counting. The Mayans used base 20. The Babylonians used base 60, which is unusual, and we'll get to them in a moment. But the rest, 10s or 20s, fingers and toes. Our entire mathematical universe is shaped by the fact that mammals evolved with a specific number of digits. If evolution had gone slightly differently and we'd ended up with 8 fingers, we'd probably all be using base 8 right now. Computers would feel much more intuitive to us, because computers already use base 2 and base 16, and base 8 would be halfway between. All the math would work out the same, but everything would look completely different. Your fingers decided what numbers look like. Alright, and next we have Fact 4. The ancient Sumerians, who lived in what's now Iraq, started writing down numbers around 3000 BC. And the reason they did it wasn't because they loved math, it was because they had too much grain. Mesopotamia had incredibly fertile land between the Tigris and Euphrates rivers, and these civilizations were producing so much agricultural surplus that they couldn't keep track of it all in their heads anymore. Taxes, trade, wages, storage, all of it needed recording. The first written numbers in human history were essentially accounting spreadsheets. The very first math was bookkeeping. The first things ever written down were receipts. Which brings us to fact 5. The Babylonians, who came after the Sumerians in the same region, used a base 60 number system, and they didn't use 60 different symbols the way you'd expect. That would have been impossible to memorize. Instead, they used 2 symbols, one for 1 and one for 10, and they combined those symbols in a positional way, so that the position of a digit told you what power of 60 to multiply it by. It was clever, and it worked well enough to do genuinely sophisticated mathematics. The reason 60 was chosen is still debated. One good guess is that 60 has an unusually large number of divisors, and it can be divided cleanly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That makes fractions much easier to work with, which mattered a lot when you were doing things like dividing grain rations between different numbers of workers. And the legacy of 60 is still all around us. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. The Babylonians decided those things about 4,000 years ago, and we just kept them. And this is where fact 6 comes in, because the Babylonian number system had a problem. There was no 0. This might sound like a minor inconvenience, but it was a serious structural flaw. Without a 0, there was no way to tell the difference between, say, the number 1 and the number 60, because both looked identical, just a single small mark. The only thing that distinguished them was context, and a gap in the writing where the empty column would be. Scribes would sometimes leave a slightly larger space to signal an empty place value. That was it. That was the whole solution. This meant that a careless scribe could accidentally multiply someone's wealth by a factor of 60 just by writing something a little too close together. Moving on to fact 7. The Egyptians built one of history's other great early number systems around the same period, and they took a completely different approach. Where the Babylonians used position to give symbols different values, the Egyptians used different symbols for each power of 10, one symbol for ones, a different symbol for tens, another for hundreds, and so on up through millions. The system was additive, meaning you just drew as many symbols as you needed and added them all up. It worked. It worked well enough to build the pyramids, to calculate the volume of pyramids, to measure land and levy taxes. The Rhine mathematical papyrus, written around 1650 BC, shows Egyptian scribes working through multiplication, division, and fractions, including some genuinely clever problems about dividing loaves of bread among workers in different proportions. But the Egyptian system had a different problem. It was incredibly slow to write. The number 999 required 27 separate symbols, 9 ones, 9 tens, 9 hundreds, all drawn out. Whereas in a positional system, you'd just write 3 symbols and be done. Speed matters when you're a scribe and you have a lot of grain to account for. And next up, fact 8. The ancient Greeks were doing something completely different from both of those civilizations. Around 600 BC, the Greeks started asking a kind of question that neither the Babylonians nor the Egyptians had really asked. Not just how much of something there is, but why math works the way it does. They were interested in proof. They wanted to understand math, not just use it. Thales of Miletus, usually credited as one of the first people to approach geometry as a logical system rather than a practical trade, is supposed to have proved that any angle inscribed in a semicircle is a right angle. Whether he actually proved it the way we'd recognize as a proof today is debatable, but the instinct was there. You don't just measure things, you reason about them. That shift from using math to understanding math changed everything. Right, fact 9. Pythagoras, who came a bit later and is much more famous, may not have proved the theorem named after him. The relationship between the sides of a right triangle, that the square of the longest side equals the sum of the squares of the other 2 sides, was known to the Babylonians at least 1,000 years before Pythagoras was born. The clay tablet known as Plimpton 322, which dates to around 1800 BC and is now at Columbia University, contains a list of Pythagorean triples, sets of 3 whole numbers that satisfy the theorem perfectly. Whoever made that tablet knew about the relationship. What Pythagoras and his followers may have contributed is not the discovery, but the proof. A logical chain of reasoning that shows why it must be true for every right triangle, not just the ones you've checked. That distinction between measuring and proving is the Greek gift to mathematics. The Pythagorean school was, by the way, a genuinely strange organization. It was part mathematical society, part cult. Pythagoreans believed that numbers were the substance of all reality. They had a strict communal lifestyle, dietary rules, and apparently a strong prohibition against eating beans. The exact reason for the bean rule has been lost to history, which is probably for the best. And that gets us to fact 10, which is about something that the Pythagoreans discovered and that absolutely horrified them. The square root of 2, the length of the diagonal of a square with sides of length 1, cannot be written as a fraction. It's what we now call an irrational number, meaning it goes on forever as a decimal without ever settling into a repeating pattern. 1.4141213562373 and on and on. This was a crisis. The Pythagoreans believed all of reality was built from ratios of whole numbers. That was the whole philosophy. And here was a length that clearly existed. You could draw it, it was right there on the page, that couldn't be expressed as any ratio of any two whole numbers, no matter how large. There's a story, almost certainly apocryphal, that a member of the Pythagorean school named Hippasus proved the irrationality of the square root of 2 while out at sea, and that his fellow Pythagoreans drowned him for it. Whether or not that's true, the irrationals were deeply uncomfortable for Greek mathematics for a long time. They threw a wrench into the whole philosophy. Next, let's look at fact 11. Euclid, who lived around 300 BC in Alexandria, pulled everything together. His 13-volume work, The Elements, is one of the most successful textbooks ever written. It was in active use in schools for over 2,000 years. The Elements starts from 5 simple assumptions called axioms or postulates, and builds essentially all of classical geometry from those 5 starting points, one proof at a time, in careful logical order. The 5 postulates include things like you can draw a straight line between any 2 points and all right angles are equal to each other. Simple, almost boringly obvious. But from those 5 things, Euclid derives the entire geometry of flat surfaces, including circles, triangles, squares, polygons, proportions, and the construction of regular solids. The 5th postulate, though, the one about parallel lines, was different from the rest. It felt a little more complicated, a little less obviously self-evident, and mathematicians spent 2,000 years trying to prove it from the other 4, convinced it could be done. That struggle, and what eventually happened when people gave up trying, is one of the great stories in mathematics, and we'll get there eventually. On to fact 12. Archimedes, who lived around the same period as Euclid, calculated the value of pi with remarkable accuracy using only geometry and careful reasoning. His method was to draw a polygon inside a circle and another polygon outside the circle, and then calculate the perimeters of those polygons. The circle's circumference had to be somewhere between those 2 values. He kept adding more sides to the polygons, squeezing the estimate tighter and tighter until he could say with confidence that pi was between 22/7 from above and a slightly smaller value from below. Pi to that level of precision, 3.14, give or take a little. Not bad for 2,000 years ago, with no calculator, no computer, no decimal notation, just a sharp mind and an afternoon. Archimedes also worked out the relationship between the volume of a sphere and the volume of the cylinder that just barely fits around it. And he was apparently so proud of this that he asked for a diagram of a sphere inside a cylinder to be carved on his tombstone. When the Roman general Marcellus captured Syracuse and ordered Archimedes be found and brought to him, the soldier who found him reportedly killed him on the spot because Archimedes was in the middle of a geometry problem and refused to come along yet. Marcellus was reportedly very upset about the death, not the geometry problem. Now, Fact 13. Meanwhile, in India, mathematics was going in a slightly different direction. Indian mathematicians, particularly those working within the traditions of Jain and Hindu astronomy, were deeply interested in very large numbers and very small ones. The Jain mathematical texts discuss numbers going up into the billions and the trillions, far beyond what anyone in Greece was formally working with. They also developed some early ideas about what would eventually become calculus, including intuitions about infinite series and the way you could add up infinitely many things and get a finite result. But the thing India did that changed everything, the thing that genuinely reorganized human civilization, was the invention of zero as a number. And here's fact 14. Zero was a long time coming, and it came in stages. The Babylonians had a placeholder 0, a symbol that meant nothing goes here. The Mayans independently developed a 0 of their own, but 0 as an actual number, something you can do arithmetic with, something you can add and subtract and multiply, that was a distinctly Indian development. The first person to give 0 formal mathematical rules was a mathematician named Brahmagupta, who wrote his rules down in 628 AD. His rules cover what happens when you add 0 to something, subtract 0, and multiply by 0. Some of them are completely correct by today's standards. A few of them, specifically his attempt to divide by 0, did not work out, and Brahmagupta got that one wrong. But he was the first person to try, which is more than most. The Sanskrit word for 0 was shunya, meaning empty. The Arabic word borrowed from the Indian concept was sifr, meaning nothing. That became the Latin zephyrum, then the Italian 0. The word cipher, which we now use to mean a secret code, comes from the same root, because to people first encountering this new number system, the 0 seemed mysterious and almost magical. So, fact 15. Once India had 0 as a number and the decimal positional system in place, meaning each column has a value 10 times the column to its right, arithmetic became dramatically faster. Try multiplying two large numbers together using Roman numerals. Actually, don't, because it's extremely tedious and there's no clean algorithm for doing it. The Roman system was additive. X means 10, X means 20, L means 50, C means 100, and while it's fine for recording totals, it's genuinely painful to compute with. The Hindu-Arabic numeral system, the one with the digits 0 through 9 that you've been using your whole life, reached Europe largely through a man named Leonardo of Pisa, who you probably know better as Fibonacci. Which brings us to fact 16. Fibonacci published a book in 1202 called the Liber Abaci, which translates roughly to the Book of Calculation. The book's main job was to introduce the Hindu-Arabic numeral system to European merchants, and it did that job very well over the following century or two. But Fibonacci also included a famous puzzle about rabbits. The puzzle goes like this. Start with one pair of rabbits. Every month, a mature pair of rabbits produces a new pair. A pair becomes mature after 1 month. How many pairs do you have after a year? The answer is a sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Each number is the sum of the two before it. Fibonacci didn't discover this sequence. It appears in Indian mathematical texts written more than 1,000 years earlier, in the context of counting patterns in Sanskrit poetry. But Fibonacci popularized it in Europe, and that's why it carries his name. The sequence seems to have nothing to do with nature, and then you look at a sunflower, and suddenly it's everywhere. Alright, and next we have fact 17. The seeds in a sunflower head are arranged in 2 sets of spirals, one set going clockwise and one going counterclockwise. Count the spirals going clockwise and you'll almost always get a Fibonacci number. Count the ones going counterclockwise and you'll get an adjacent Fibonacci number. This isn't decoration. It's the most efficient packing arrangement that a growing plant can achieve, given that each new seed grows at a fixed angle relative to the previous one. The golden angle, the angle that produces the most efficient packing, is approximately 137.5 degrees, and that number is tied directly to the golden ratio, which is tied directly to the Fibonacci sequence. The connection runs all the way down to how cells divide and how growth works at the biological level. Same thing happens with pine cones and pineapples, and the way leaves spiral around the stem, arranging themselves to catch the maximum amount of sunlight without blocking each other. Fibonacci numbers are what you get when living things optimize their own growth. Now, fact 18. The golden ratio is the number approximately 1.618, usually written as phi. Take any 2 consecutive Fibonacci numbers and divide the bigger one by the smaller one. 5 divided by 3 is 1.667. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. As you go further out in the sequence, the ratio gets closer and closer to 1.618, but it never arrives there exactly. Pi is irrational. It never settles into a pattern. Pi has the unusual property of being the number most difficult to approximate with a fraction. Every other irrational number can be expressed as a fraction that comes reasonably close. Pi, for example, can be approximated as 355 over 113, and that fraction is accurate to within less than 1/10 millionth. But phi? The best rational approximations to phi are consecutive Fibonacci numbers, and those converge agonizingly slowly. This property, being maximally hard to pin down with fractions, is actually why phi appears in plant growth. If a plant tried to use any other angle, seeds placed at that angle would line up too perfectly with earlier seeds and create gaps. Phi is the least periodic angle, the one that fills space most evenly. And that leads us to fact 19. There are claims that the golden ratio appears in human art and architecture going back to the Parthenon and the pyramids and Leonardo da Vinci. Most of those claims are exaggerated, and some of them are simply wrong. Mathematicians who have actually measured the Parthenon find that its proportions are close to the golden ratio in some places, close to other simple ratios in other places, and a choice of which measurements to report tends to depend on what the person measuring is hoping to find. The golden ratio is close enough to 3 to 2 and 5 to 3 and 8 to 5 that it's easy to find it if you squint at almost anything. What's true is that the golden ratio has genuinely interesting mathematical properties. What's probably not true is that ancient architects consciously designed buildings around it, or that the human face is governed by phi, or that the golden ratio is objectively beautiful. The beauty claims have no strong empirical support. The math, though, is interesting in its own right, without needing to be cosmic. So let's get to fact 20, and let's talk about something that doesn't show up in sunflowers at all: algebra. The word algebra comes from Arabic. The full phrase is al-jabr, which means something like the reuniting of broken parts, and it appears in the title of a book written around 820 AD by a Persian mathematician named Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi's book, the compendious book on calculation by completion and balancing, laid out systematic methods for solving equations. The particular innovation was treating unknown quantities as objects you could manipulate symbolically, moving them from one side of an equation to the other, completing squares, simplifying. The techniques themselves weren't entirely new, but the organization and clarity were. The word algorithm, the process you follow step by step to compute something, comes from a Latinized version of al-Khwarizmi's own name. He is, in a very real sense, the person algorithms are named after. Every time someone talks about a social media algorithm or a search algorithm, they're invoking an 800-year-old Persian mathematician. On to fact 21. The Islamic Golden Age, roughly from the 8th through the 13th century, produced an extraordinary amount of mathematics that Europe wouldn't catch up with for centuries. Scholars working in Baghdad, Cairo, Cordoba, and other centers of learning translated Greek mathematical texts into Arabic, preserved them, extended them, and in many cases corrected them. The translation movement meant that works like Euclid's Elements, which existed in few copies in Europe, were being actively studied, discussed, and built upon in the Arabic-speaking world. Mathematicians like Al-Kindi, Ibn al-Haytham, and Omar Khayyam, who is better known in the West as a poet, were making serious contributions to number theory, optics, and the algebraic solution of cubic equation. Khayyam found geometric methods to solve cubic equations, which nobody in Europe would match for another 500 years. Next up, Fact 22. Around the same time that Europe was just beginning to rediscover Greek mathematics, the Maya civilization in Central America had developed a remarkably sophisticated system on their own. Maya mathematics used base 20, counting by 20s instead of 10s. Their number system required only 3 symbols: a dot for 1, a bar for 5, and a shell shape for 0. You combine those 3 symbols to write any number in a positional system. The Maya 0, represented by that shell glyph, was one of the few independently invented zeros in human history. The Olmec people, an earlier Mesoamerican civilization, had used a placeholder for 0 by around 38 BC, predating the Indian formalization by several centuries. The Maya used their mathematical system primarily for astronomy and their elaborate calendar system. Their astronomical calculations, including the length of the solar year and the movements of Venus, were accurate to a degree that still impresses astronomers today. Moving on, Fact 23. Europe picked up mathematics seriously, again starting in the 12th century, largely through translation. The works of Greek mathematicians like Euclid and Archimedes, preserved in Arabic translation, were translated into Latin in Spain and Sicily, the contact points between the Islamic world and Europe. So, mathematics came back to Europe by a roundabout route: Greek texts translated into Arabic, translated into Latin, read by European scholars who thought they were encountering ancient wisdom, but were actually reading scholarship that had been extended and refined over several hundred years of Islamic mathematics. This borrowing happened without a lot of credit being given, which has led to a distorted picture of mathematical history in some traditions. And that brings us to Fact 24. René Descartes, the French philosopher who said, "I think, therefore I am," gave mathematics something it had been missing: a way to connect algebra and geometry. Before Descartes, algebra and geometry were essentially separate subjects. You proved geometric things with geometric methods, and you solved algebraic equations with algebraic methods, and there wasn't a clean bridge between them. Descartes' idea, published in 1637 as an appendix to his philosophical work Discourse on Method, was to assign numbers to positions in space, lay down 2 perpendicular lines, call them x and y, and now every point in the plane has an address, a pair of numbers. With this system, the Cartesian coordinate system, named after him, every geometric shape becomes an equation, and every equation becomes a shape. A circle with radius 2 centered at the origin is every point that satisfies the equation x squared plus y squared equals 4. A straight line is a linear equation. A parabola is a quadratic. This unification meant that tools from algebra could be used to solve geometric problems, and geometric intuition could illuminate algebraic ones. It's one of the most powerful ideas in the history of mathematics, and it came as an appendix to a philosophy book. Right, fact 25. There's a small detail about the square root symbol that traces back to the printing industry. The symbol for square root may have originated from a lowercase r, an abbreviation of the Latin word radix, meaning root, or it may have been a completely different symbol that just got standardized over time. The exact origin is disputed, but Descartes, in his own work, popularized a version of the symbol by adding the bar on top, the vinculum, to make clear what the root applies to. Before that, it was sometimes ambiguous. There's a story, possibly true, that the specific shape of the symbol was partly influenced by what Descartes' printer could physically produce. Typography shaped mathematics. The symbols we use to think about numbers were partly chosen by whoever happened to be setting the type. Next up is fact 26, and this one is the invention of calculus, which is one of the most consequential and also most contentious events in mathematical history. The basic problem calculus solves is this: how do you find the instantaneous rate at which something is changing? Not the average speed over a trip, but the exact speed at one specific moment. Not the average slope of a curve, but the slope at a single point. And how do you find the area under a curve, the length of an arc, the volume of an irregular solid? These problems had been circling around mathematics for centuries. Archimedes made progress. Indian and Islamic mathematicians made progress. Johannes Kepler used methods that were close to calculus to figure out the orbits of planets. And then, independently, within a few years of each other, both Isaac Newton and Gottfried Wilhelm Leibniz worked out a complete systematic calculus. And then they spent the rest of their lives in a brutal dispute about who did it first. Which naturally takes us to fact 27. Newton developed his version of calculus, which he called the method of fluxions, in the mid-1660s, during a period when Cambridge University was closed because of the plague. He went home to Lincolnshire, had essentially nothing to do, and apparently used the time to lay the foundations for calculus, develop his theories of gravity and motion, and work out the nature of color and light, all in roughly 18 months. Newton, being Newton, didn't publish any of it for decades. This was a pattern with him. He had an almost pathological reluctance to publish and expose his work to criticism. Leibniz, working in Germany in the 1670s, developed his own version independently. His notation was different from Newton's, and in some ways more elegant. The dx and dy notation that we still use today comes from Leibniz, not Newton. Leibniz published first. Newton then claimed priority. The dispute got ugly, involving accusations of plagiarism from both sides, committee investigations, and decades of poisoned correspondence between European mathematical communities. The current consensus among historians is that both men genuinely invented calculus independently, but the dispute damaged international mathematical progress for a generation because British mathematicians loyally stuck with Newton's inferior notation, while continental Europe used Leibniz's better system. And here's fact 28. Calculus rests on a concept called a limit. The basic idea: imagine you want to find the slope of a curve at a single point. A slope requires 2 points, rise over run. But a single point is just a single point. So you take 2 points on the curve, one being your target point and the other nearby, and calculate the slope between them. Then you move the second point closer to the first, and closer still, as close as you like without them actually touching. The slope of the line between them settles toward a specific number, and that number is the slope at your target point. That settling toward a specific value is a limit, and limits, formalized properly, are the foundation on which all of calculus is built. Newton and Leibniz both had the intuition. Making it rigorous took another century of work, mostly by the French mathematician Augustin Louis Cauchy in the early 1800s. Moving on to fact 29. The number e, approximately 2.71828, is the base of the natural logarithm. It appears naturally as the answer to a question about growth. If you have an investment paying 100% interest per year, and you compound that interest continuously, not once a year, not once a month, but at every instant, the factor by which your money grows in a year approaches e. The more often you compound, the closer you get to e. Once per year, 2. Twice per year, 2.25. Monthly, about 2.61. Daily, about 2.714. Every second, even closer to 2.71828. You never quite reach it, and you never go past it. E shows up in the mathematics of radioactive decay, population growth, the shape of a hanging chain, the distribution of errors in measurements, the probability of certain events. It's one of the most common numbers in the mathematical description of how things change over time. All right, fact 30. And this one is what is often called the most beautiful equation in mathematics: Euler's identity. Leonhard Euler, the Swiss mathematician who is probably the most prolific mathematician in history, and we'll get to him properly in a moment, published this identity in the 18th century. It says e to the power of I times pi plus 1 equals 0. That equation contains 5 of the most important numbers in all of mathematics, 0, 1, e, I, which is the square root of -1, and pi. They're connected by the three most fundamental operations: addition, multiplication, and exponentiation. And the equation, which looks like it should be impossible, is not only true, but is a consequence of a broader formula that turns out to be incredibly useful in physics, engineering, and signal processing. The physicist Richard Feynman, as a teenager, came across Euler's formula and described it in his notebook as the most remarkable formula in mathematics. When asked later about his favorite equation, the physicist Max Tegmark said Euler's identity made him feel the way other people feel when they hear a perfect piece of music. And that leads us into fact 31, which is about I, the square root of -1. The problem with square roots of negative numbers is that no ordinary number squared gives you a negative result. Positive times positive is positive. Negative times negative is positive. You can't get to a negative by squaring anything in the real number system. For a long time, this meant that equations with square roots of negative numbers were just considered to have no solution. Then, starting around the 16th century, Italian mathematicians working on cubic equations started noticing that if you just pretended the square root of -1 was a number, called it I, and carried it through your calculations, you often got real correct answers at the end, even if I vanished along the way. This was disturbing. Why should using a number that doesn't exist give you correct, real answers? The answer, worked out over the next 2 centuries, is that imaginary and complex numbers, combinations of real numbers and multiples of I, form a complete, consistent mathematical system that extends the real numbers in a perfectly coherent way. They're not less real than real numbers. They're just differently real. And they turn out to be essential in quantum mechanics, electrical engineering, fluid dynamics, and signal processing. Descartes, who coined the word imaginary for these numbers, meant it as a dismissal. He was wrong. Next, fact 32. Leonhard Euler lost the sight in one eye in his 20s and went almost completely blind in his other eye in his 50s. He continued doing mathematics. In fact, his output actually increased after he went blind, because he no longer had the distraction of reading and correspondence. He would dictate to secretaries, working problems in his head with extraordinary precision. He produced roughly 900 books and papers over his lifetime, covering number theory, graph theory, mechanics, optics, and music theory. His collected works would fill somewhere between 60 and 90 volumes, depending on how you count. The mathematical notation we use today is largely Euler's. The letter E for the natural base, the letter I for the imaginary unit, the Greek letter pi for the circle constant, the use of the letter F with parentheses for functions. Euler standardized all of these. and they've stuck. And here's fact 33. Euler also invented graph theory, essentially by accident, by thinking about a puzzle in the Prussian city of Königsberg, which is now Kaliningrad in Russia. Königsberg was built on two islands in the Pregel River, connected to each other and to the river banks by 7 bridges. A popular question among the citizens was whether you could take a walk that crossed each bridge exactly once. Euler proved in 1736 that no such walk was possible, and in doing so, he created an entirely new branch of mathematics. His key insight was to strip away all the irrelevant detail, the actual geography of Königsberg, the distances between bridges, the names of streets, and reduce the problem to just a diagram of nodes, which are landmasses connected by edges, which are bridges. Then he asked, under what conditions can you traverse every edge exactly once? The answer depends only on how many edges connect to each node. If more than 2 nodes have an odd number of connections, no such path exists. Königsberg had 4 nodes with odd numbers of connections, so no walk was possible. That abstract diagram of nodes and edges is a graph. Graph theory is now the mathematical foundation of social network analysis, route planning, the internet, circuit design, and much of modern computer science. On to fact 34. Prime numbers are numbers greater than 1 that can only be divided evenly by themselves, and 1, 2, 3, 5, 7, 11, 13, 17, 19, 23. The sequence continues forever, becoming gradually more sparse as you go higher, but never stopping entirely. Euclid proved that there are infinitely many primes around 300 BC, using one of the most elegant proofs in all of mathematics. The argument goes like this. Suppose there are only finitely many primes. Write them all down as a list. Now multiply all of them together and add 1. That new number is either prime itself, in which case it's a prime not on your list, contradicting the assumption, or it has a prime factor. But none of the primes on your original list can divide it evenly, because dividing any of them into your new number leaves a remainder of 1. So either way, you have a prime not on your list. Contradiction. Therefore, there must be infinitely many primes. That proof is over 2,000 years old, and it's still exactly right. Now, fact 35. No mathematician has ever found a formula that produces only prime numbers. There are patterns, partial patterns, and approximations, but nothing exact. The prime numbers are distributed among the whole numbers in a way that looks random from close up, but follows a statistical pattern when you step back. The prime number theorem, proved independently by Hadamard and de la Vallée-Poussin in 1896, says that the number of primes up to n is approximately n divided by the natural logarithm of n. So, around the number 10 million, about 1 in every 16 numbers is prime. Around a billion, 1 in about 20. But which specific numbers are prime has no simple pattern. They just are what they are. which gets us to fact 36. The Riemann hypothesis is probably the most famous unsolved problem in mathematics. Bernhard Riemann, a German mathematician, published a paper in 1859 in which he described a function now called the Riemann zeta function and stated a guess about where that function equals 0. The guess that all non-trivial zeros of the function have a real part of exactly 1/2 has been checked for trillions of zeros. All of them satisfy it. Nobody has found one that doesn't, and nobody has proved that they all must. The Riemann hypothesis is deeply connected to the distribution of prime numbers. If it's true, our understanding of how primes are distributed becomes much sharper. If it's false, if someone someday finds a zero that breaks the rule, it would upend a century and a half of mathematics that has quietly assumed the hypothesis is correct. The Clay Mathematics Institute will pay $1 million to whoever proves or disproves it. It's been on their list since the year 2000. Nobody has collected. Next up, fact 37. There are exactly 4 numbers for which the sum of the cubes of the digits equals the number itself. 1 cubed is 1, 153. 1 cubed plus 5 cubed plus 3 cubed equals 1 plus 125 plus 27, which equals 153. 370 has the same property. So does 371 and 407. These numbers are called narcissistic numbers. There are exactly 4 3-digit narcissistic numbers. Go up to 4 digits and there are 3. Go up to 7 digits and there are none. Mathematicians have checked up to a certain point and believe there are only a finite number of narcissistic numbers total, 88 of them, the last being a 39-digit number that when you cube each of its digits and add them all up, you get the number back. Nobody engineered this, it's just how the digits happen to interact. And that brings us to fact 38. 6 is the smallest perfect number. A perfect number is one where the sum of all its divisors, not counting itself, equals the number. 6 is divisible by 1, 2, and 3. 1 plus 2 plus 3 equals 6. The next perfect number is 28. 1 plus 2 plus 4 plus 7 plus 14 equals 28. After that, 496. Then 8,128. After that, the perfect numbers get very large very quickly. Nobody knows if there are infinitely many perfect numbers. All known perfect numbers are even. Nobody has ever found an odd perfect number, but nobody has proved that one doesn't exist. This has been an open question since Euclid. Moving right along, fact 39. The Collat's conjecture is one of the simplest to state unsolved problems in mathematics. Take any positive whole number. If it's even, divide by 2. If it's odd, multiply by 3 and add 1. Repeat the process with whatever you get. The conjecture says you will always eventually reach 1. Try it with 6. 6 is even, so 3. 3 is odd, so 10. 10 is even, so 5. 5 is odd, so 16. 16 to 8 to 4 to 2 to 1. Done. Try any number. Every number anyone has ever tried eventually reaches 1. The sequence has been verified computationally for numbers up to an absolutely staggering height, at least up into the quintillions and beyond. Nobody has proved it must always happen. The mathematician Paul Erdos, who we'll meet properly in a moment, said about the Collat's conjecture, "Mathematics is not yet ready for such problems. It remains unsolved today." Now, fact 40. Paul Erdos himself is worth pausing on. He was a Hungarian mathematician who lived from 1913 to 1996, and he might have been the most socially unusual mathematician in a field not short of unusual characters. He had no permanent home. He traveled with 2 suitcases his entire adult life, showing up at the homes and offices of collaborators around the world, expecting to be put up and fed and mathematically engaged. You would arrive at someone's door and say, "My brain is open," and then they'd work on problems together. He published more papers than almost any mathematician in history, over 1,500, and he had so many collaborators that mathematicians invented the concept of an Erdos number. If you wrote a paper with Erdos directly, your Erdos number is 1. If you wrote a paper with someone who wrote a paper with Erdos, your Erdos number is 2. The average Erdos number of professional mathematicians is about 5. Erdos had strong opinions about which proofs were elegant and which were not. When a proof was particularly beautiful, he said it was from the book, a theoretical book that God kept, containing the most perfect proof of every theorem. And next, we have fact 41. Erdos also believed, somewhat eccentrically, that children were humanity's closest thing to pure mathematical creativity, because they hadn't yet been taught to stop asking naive questions. The naive question is often the most important one. The Collat's conjecture looks like something a child would ask. Goldbach's conjecture, the still unproven idea that every even number greater than 2 is the sum of 2 primes, is something you could explain to someone in 30 seconds. Fermat's last theorem, which tortured mathematicians for 350 years, can be stated in one sentence. The most profound mathematical questions have simple surfaces and bottomless depths. Which takes us to fact 42. Fermat's last theorem says that there are no positive whole numbers a, b, and c that satisfy the equation a to the nth power plus b to the nth power equals c to the nth power, when n is any whole number greater than 2. For n equals 2, solutions exist. Those are Pythagorean triples, like 3 squared plus 4 squared equals 5 squared, which is 9 plus 16 equals 25. But for n equals 3, or 4, or any higher power, there are no solutions at all. Pierre de Fermat, the 17th century French lawyer and amateur mathematician, wrote this claim in the margin of his copy of an ancient Greek text with the note, "I have discovered a truly marvelous proof of this, which this margin is too narrow to contain." That margin, note, haunted mathematics for 357 years. All right, fact 43. Pierre de Fermat, by the way, was not a professional mathematician. He was a lawyer, a good one by all accounts, a judge, eventually, in southern France. Mathematics was his hobby. He did it in the evenings. He corresponded with other mathematicians but rarely published formally. Many of his results were communicated in letters, and the proofs he claimed to have were often sketchy or left entirely to the reader to work out. Fermat's last theorem was eventually proved, finally, completely, rigorously, by the British mathematician Andrew Wiles in 1994. The proof runs to over 100 pages and uses mathematical tools that Fermat couldn't possibly have had access to in the 17th century. Either Fermat's marvelous proof was flawed in some way he didn't notice, or he was lying, or he was just wrong. Most mathematicians suspect the first option. And here's fact 44. Wiles had been working on the proof in secret for 7 years before announcing it. He had found the problem in a library book as a 10-year-old child and never forgotten it. When he finally had the mathematical tools he needed, including a connection to elliptic curves and something called the Taniyama-Shimura conjecture that had been identified by other mathematicians, he retreated to his attic and worked essentially alone. In 1993, he announced the proof at a lecture in Cambridge. The audience, aware they were watching something extraordinary, gave him a standing ovation. Then, in the process of peer review, a flaw was found. Wiles spent another year fixing it, in anguish. In 1995, the corrected proof was published. He said later that the year between the announcement and the corrected proof was the most emotionally difficult of his life. Next up, fact 45. The development of non-Euclidean geometry in the 19th century is one of the cleaner examples in math of a problem being solved by completely abandoning the assumptions that made it a problem. Remember Euclid's fifth postulate, the one about parallel lines that nobody could prove from the other four? Mathematicians kept trying because they were sure it had to follow logically from the others. 2,000 years of trying. Then, in the early 19th century, mathematicians Nikolai Lobachevsky and Janos Bolyai independently asked a different question. What if the fifth postulate is just wrong? What if parallel lines can meet? What if, through a given point, there are infinitely many lines parallel to a given line? The resulting geometry is perfectly consistent. It's just the geometry of curved surfaces, like the surface of a sphere. On a sphere, straight lines are great circles, and any two great circles eventually meet. Triangles on a sphere have angles that add up to more than 180 degrees. None of this contradicts the other four postulates. The discovery blew open the concept of geometry itself. Geometry doesn't have to be the geometry of flat space. There are infinitely many geometries, each internally consistent, each describing a different kind of space. Einstein, several decades later, would need exactly this insight. The geometry of space-time near a massive object is non-Euclidean. Moving on to fact 46. The 19th century also saw the formalization of statistics as a mathematical discipline. The basic ideas, averages, frequencies, the idea of probability had been around for a long time. Gambling motivated a lot of it. Blaise Pascal and Pierre de Fermat, who also crops up here, corresponded in 1654 about how to fairly divide a pot of money when a gambling game is interrupted before it finishes. That exchange is often cited as the birth of probability theory. But statistics, as a way of understanding populations and making systematic inferences about the world, became enormously important in the 19th century, driven partly by the needs of governments collecting census data, partly by the insurance industry, and partly by astronomers who needed to deal with measurement errors in a principled way. Carl Friedrich Gauss, trying to figure out the best way to combine noisy astronomical observations, worked out the method of least squares, which means finding the line or curve that minimizes the total squared error. The bell curve, sometimes called the Gaussian distribution, is named after him because he was among the first to work out its mathematical properties fully. And that gets us to fact 47. The normal distribution, the bell curve, shows up in nature so often that it can feel like a conspiracy. The heights of people in a population follow a bell curve. The errors in careful measurements follow a bell curve. The scores on many standardized tests follow a bell curve. The result of flipping a coin 1,000 times and counting heads follows a bell curve. The reason for this is a theorem called the central limit theorem, which says that when you add up many independent random things, even things that are individually not bell-curved at all, the total tends to follow a normal distribution. Roll one die, uniform distribution, every value equally likely. Roll 100 dice and add them up. The total is approximately normally distributed. The central limit theorem is one of the reasons statistics works at all. It's why you can take a sample of a population and make reasonable inferences about the whole without needing to measure everyone. Now, fact 48, and this is where things get much stranger. Georg Cantor was a German mathematician who, in the 1870s and 1880s, took seriously the question of how big infinity is. Before Cantor, infinity was mostly treated as a philosophical concept, a direction rather than a size. Things could go on forever, but the question of whether some infinities were bigger than others wasn't really on the mathematical table. Cantor put it on the table and then turned the table over. His key tool was the idea of one-to-one correspondence. Two sets have the same size if you can pair up their elements perfectly, 1-to-1, with nothing left over. You don't need to know how many elements are in either set. You just need to know whether the pairing is possible. On to fact 49. The first surprising result: the set of all even numbers is the same size as the set of all whole numbers. This feels wrong. There are clearly half as many even numbers as whole numbers, right? Well, over any finite stretch, sure. But over all the whole numbers, you can pair them up perfectly. Pair 1 with 2, pair 2 with 4, pair 3 with 6, pair 4 with 8, pair 5 with 10. Every whole number gets paired with exactly one even number, and every even number gets paired with exactly one whole number. No leftovers, same size. Cantor said these infinite sets have the same cardinality, the same infinite size, which he called Aleph 0, the smallest infinite cardinal. This bothered people. His colleague Leopold Kronecker called him a corrupter of youth. The French mathematician Henri Poincare described Cantor's work as a disease from which mathematics would eventually recover. Some religious thinkers objected on the grounds that actual infinity was divine and shouldn't be subject to mathematical analysis. Cantor was bothered by the opposition. He suffered serious depression throughout his life, and the struggle against the mathematical establishment contributed to it. Which brings us to fact 50. Then Cantor showed that some infinities are genuinely, irrefutably bigger than others. The set of all real numbers, all the numbers on a continuous number line, including all the decimals and irrationals and whatever else, is larger than the set of all whole numbers. Provably, rigorously, definitively larger. The proof is simple enough to sketch. Suppose you try to list all the real numbers between 0 and 1 in a numbered list. Line 1 might be 0.3456. Line 2 might be 0.7812, and so on. Cantor showed that no matter how clever your list is, you can always construct a real number not on it. How? Take the first digit of the first number on your list, change it. Take the second digit of the second number, change it. The third digit of the third number, change it. The number you've constructed differs from every number on the list because it differs from the first number in the first decimal place, from the second number in the second decimal place, and so on. So your list is incomplete. Any list is incomplete. You cannot list all the real numbers. This is Cantor's diagonal argument, and it proves that the real numbers are uncountably infinite, bigger than countably infinite, and that there are at least two different sizes of infinity. And next, fact 51. It turns out there are infinitely many different sizes of infinity. For any infinite set, the set of all its subsets, the power set is strictly larger. This gives you an escalating hierarchy. Aleph 0, then a bigger infinity, then a bigger infinity still, and so on, with no top. Cantor spent years trying to figure out whether there was an infinity between Aleph 0 and the cardinality of the real numbers. He suspected there wasn't, and this suspicion became the continuum hypothesis. He could never prove it. Right, fact 52. The continuum hypothesis has a remarkable status in mathematics. It is neither provable nor disprovable. This is not a practical limitation, like it's very hard and we haven't found the proof yet. It's a deep impossibility. Kurt Gödel proved in 1940 that the continuum hypothesis is consistent with the standard axioms of mathematics, meaning you can't derive a contradiction from it. And Paul Cohen proved in 1963 that the negation of the continuum hypothesis is also consistent, meaning you can't derive a contradiction from assuming it's false either. The continuum hypothesis is independent of the axioms. Within standard mathematics, you cannot settle it. Both the world where it's true and the world where it's false are equally valid mathematical universes. Moving on, fact 53. Gödel's incompleteness theorems from 1931 are possibly the most philosophically disorienting results in mathematical history. Gödel proved that any mathematical system strong enough to describe basic arithmetic, if it's consistent, meaning it doesn't contain contradictions, must be incomplete. There will always be true mathematical statements that cannot be proved within the system. Not we haven't found the proof yet. Definitely, provably, cannot be proved from within the system. No matter how many axioms you add, no matter how clever your reasoning, there will always be some true things you can't reach. Gödel was 25 years old when he proved this. Mathematicians of the era had been working on a program, Hilbert's program, named after the great German mathematician David Hilbert, to establish all of mathematics on a complete, consistent, provable foundation. Gödel showed that this program was impossible in principle. Hilbert was reportedly speechless. The dream of a mathematical theory of everything, a finite set of axioms from which all mathematical truth could be derived, died in 1931. And here's fact 54. To prove his incompleteness theorem, Gödel did something almost impossibly clever. He encoded mathematical statements as numbers. He assigned a number to each symbol, each variable, each operation, and then used those numbers to turn any mathematical statement into a single, very large number. Then he showed that some properties of mathematical proofs could be encoded as properties of those numbers. He essentially made mathematics talk about itself using the language of arithmetic. The key statement he constructed was something like, "This statement is not provable. If the statement is provable, then it's a true statement that says it's not provable, which is a contradiction If it's not provable, then it's a true statement about mathematics that math cannot prove. Either way, there's a true statement that can't be proved. This is related to the ancient liar's paradox. This sentence is false, but encoded in pure mathematics with rigorous precision. Next up, fact 55. Gödel's incompleteness result has a sibling, the halting problem, proved by Alan Turing in 1936. Turing, who would go on to be one of the founders of computer science, asked, "Is there a general method that can look at any computer program and determine whether it will eventually stop or whether it will run forever?" He proved there isn't. No algorithm can solve the halting problem for all possible programs. This result is related to Gödel's. If you could solve the halting problem, you could prove all mathematical truths, which Gödel already showed was impossible. Turing proved the halting problem's unsolvability by a clever self-referential argument. Suppose you had a machine that could determine whether any program would halt. Feed that machine its own description as input. What happens? A contradiction follows inevitably. The halting problem is why there's no antivirus that can catch all viruses. It's a deep limitation on what computation can achieve. Which leads us into fact 56. Alan Turing also imagined in that same 1936 paper an abstract computing machine, now called a Turing machine, that could simulate any computation given enough time and memory. This was 9 years before the first practical electronic computers existed. Turing described a machine that reads symbols on an infinite tape, follows a table of rules, and moves the tape back and forth. That abstract description turned out to capture precisely what every computer ever built can do. The Church-Turing thesis says that anything intuitively computable can be computed by a Turing machine. This isn't a theorem, it's more like a definition or a philosophical claim, and it's held up remarkably well. Every model of computation that anyone has proposed, no matter how different in design, turns out to be equivalent in power to a Turing machine. Alright, fact 57. Computers, for all their speed, work in binary, meaning base 2, instead of 10 digits, 0 through 9. Binary has 2, 0, and 1. Every number is a string of zeros and ones. Every instruction, every image, every piece of music stored on a computer is ultimately a very long string of those 2 digits. The reason computers use binary isn't because base 2 is mathematically special. It's because physical systems that can reliably be in one of 2 states, a switch that's on or off, a transistor that's conducting or not, a magnetic domain pointing up or down, are easy to build. 3-state systems are harder. A 2-state system is the simplest possible reliable physical representation. The entire digital world is built on 2. And that gets us to fact 58. The number of atoms in the observable universe is estimated to be around 10 to the power of 80. That's a 1 followed by 80 zeros. If you shuffled a standard deck of 52 playing cards perfectly randomly, the number of possible orderings is 52 factorial, which is 52 times 51 times 50 times all the way down to 1. That number is approximately 8 times 10 to the power of 67. So the number of possible card orderings is a few billion times smaller than the number of atoms in the universe. That means if every atom in the universe were a card shuffler, shuffling a new deck every second since the Big Bang, they would still not have shuffled every possible ordering. Most orderings of a deck of cards have never existed and might never exist. Every properly shuffled deck is unique in the history of the universe. Moving right along, fact 59. The number 1 Google is 10 to the power of 100. It's a 1 followed by 100 zeros. Edward Kasner, a mathematician at Columbia University, coined the term in the 1930s, and he asked his 9-year-old nephew to come up with the name. Milton Sirota, the nephew, said Google. Kasner used it. There are not a Google atoms in the observable universe. There are not a Google atoms in any conceivable amount of visible matter. A Google is a number so large it has no physical meaning. There just isn't enough stuff to count that high. The company Google named itself after this number. They misspelled it, whether intentionally or by accident, has never been definitively settled. Next, fact 60. A Googleplex is 10 to the power of a Google. It's a 1 followed by a Google zeros. To write out a Googleplex in full decimal form, you would need more space than the observable universe provides. The number of atoms in the universe is nowhere near large enough to store the digits. A Googleplex cannot be written down even in principle within physical reality, and yet it's a perfectly well-defined number. Mathematics has no trouble with it. Mathematicians can reason about numbers astronomically larger than a Googleplex with no difficulty at all. This is one of the things about mathematics that's quietly strange. The size of the universe puts no practical limit on what can be talked about. And here's fact 61, which is about a number called Graham's number. In 1971, the mathematician Ronald Graham was working on a problem in an area called Ramsey theory, which is broadly about finding order within apparently disordered structures. He needed an upper bound, a number he could guarantee was at least as large as the answer, even if he wasn't sure of the exact answer. The number he came up with, now called Graham's number, is so obscenely large that ordinary exponential notation can't express it. Even the number of exponential towers you'd need can be expressed in ordinary exponential notation. There's a notation for it called Knuth's up arrow notation, and even in that notation, the number requires a definition that takes several recursive steps to describe. What makes this genuinely strange is that Graham's number is a specific, finite whole number. It's less than infinity. There are infinitely many numbers larger than it, and yet, in some deep sense, the human mind has almost no capacity to comprehend how large it is, even in the abstract. The digit in the ones place of Graham's number, however, is 7. We know that with certainty. On to fact 62. Pi is approximately 3.14159535389793. You could go further. People do go further. There are records for memorizing pi to very large numbers of decimal places, and the current record is over 100,000 decimal places memorized and recited. That took about 9 hours. There's also a competition called a haiku, where each word has a number of letters corresponding to consecutive digits of pi. May I have a large container of coffee is one of them. 3.1415926. 3.1415926. The sentence is technically a mnemonic for 8 digits of pi. Now, fact 63. Pi is irrational, meaning its decimal expansion never repeats. It was proved irrational in 1761 by Johann Heinrich Lambert. Pi is also transcendental, meaning it's not the solution to any polynomial equation with integer coefficients. This was proved by Ferdinand von Lindemann in 1882. Transcendental means, specifically, that it's not algebraic. The square root of 2 is irrational but algebraic because it satisfies x squared minus 2 equals 0. Pi satisfies no such finite polynomial. This distinction matters because it resolved the ancient problem of squaring the circle, which means constructing a square with the same area as a given circle using only a compass and straight edge. Transcendentality of pi makes this provably impossible. 2,000 years of mathematicians tried to square the circle. Lindemann proved in 1882 that they were all trying to do something that cannot be done. Which brings us to fact 64. The digits of pi appear to be random, not provably random. The conjecture that pi is normal, meaning every digit and every sequence of digits appears with the frequency you'd expect from a truly random sequence, has not been proved. But in practice, if you look at the first trillion digits of pi, each digit 0 through 9 appears roughly 1/10 of the time. There's no obvious pattern. This means that somewhere in the digits of pi, encoded in any numbering scheme you choose, is your phone number and your birthday and every book ever written and every book that could ever be written, and nonsense and everything. This sounds profound and is sometimes presented as such, but it's actually a property of any infinite non-repeating sequence of digits, not just pi. The difference is that pi is a specific, computable, geometric constant, and the idea that it contains all information inside it has a particular poetry that random strings don't. And that leads into fact 65. The number 0.99999 repeated to infinity is exactly equal to 1, not approximately equal, not approaching 1, equal. Here's one way to see it. 1 divided by 3 equals 0.3 repeating. 2 divided by 3 equals 0.6 repeating. Add them together, 1, but 0.3 repeating plus 0.6 repeating equals 0.9 repeating. So 0.9 repeating equals 1. Another way, if 0.9 repeating were less than 1, there would be a number between them. What is that number? There is no such number. There's no room for anything between them on the number line. So they must be the same point, the same number. This trips people up. It seems like 0.9 repeating is just very, very close to 1, but not quite there. But very close, but not quite, is a finite story. Infinity is different. Infinitely close is the same as equal. Next up, fact 66. There's a result called the Banach-Tarski paradox, and it is one of the more alarming theorems in mathematics. Proved by Stefan Banach and Alfred Tarski in 1924, the theorem says that you can take a solid sphere, cut it into a finite number of pieces, specifically 5 pieces, and rearrange those pieces using only rotations and translations with no stretching or distortion to produce 2 solid spheres, each the same size as the original. 1 sphere becomes 2. You don't add any material. This is not physically possible. The pieces involved are not ordinary pieces in any physical sense. They're infinitely complex, unmeasurable sets of points that can't be constructed in practice. But mathematically, using the axiom of choice, the theorem is perfectly valid. The axiom of choice is one of the standard axioms of mathematics, and it says roughly that you can always pick one element from each set in any collection of non-empty sets. This sounds innocuous. It implies Banach-Tarski. Some mathematicians are therefore uncomfortable with it. Moving on, fact 67. The axiom of choice also proves that every set can be well ordered, meaning arranged in a sequence where every non-empty subset has a smallest element. For the whole numbers, this is obvious. Just order them in the usual way. But for the real numbers, can you well order all the points on a continuous line? The axiom of choice says yes, but it gives no method for doing it. You can prove it's possible without being able to exhibit the ordering. This is a feature of non-constructive proofs that some mathematicians find deeply unsatisfying, being told something exists without being told how to find it. And here's fact 68. Topology is the area of mathematics that studies properties of shapes that survive stretching and bending, but not tearing or gluing. In topology, a coffee cup and a donut are the same shape because you can continuously deform one into the other. Both have exactly one hole. A sphere and a cube are the same shape. A figure 8 is different from a circle because a figure 8 has a crossing point that the circle doesn't. The classic topological joke is that a topologist is someone who can't tell the difference between a coffee cup and a donut. Alright, fact 69. The Möbius strip is a surface with only one side. Take a strip of paper, give it 1/2 twist, and tape the ends together. What you have is a surface where if you start drawing a line along the middle, you'll end up back where you started, having covered both sides without lifting your pen. There's only one side. If you cut it in half lengthwise, you don't get 2 loops, you get one longer loop. The Möbius strip is a perfectly physical, constructible object with a genuinely non-obvious topological property. August Ferdinand Möbius, who discovered it in 1858, was doing serious mathematics. The fact that it can be made from a strip of paper doesn't make it less remarkable. And next we have fact 70. The Poincare conjecture, proposed in 1904, asked whether every 3-dimensional shape without holes is basically equivalent to a 3-dimensional sphere. Henri Poincare, one of the great mathematicians of the early 20th century, proposed it. It sat unsolved for almost exactly 100 years. Then, in 2002 and 2003, a Russian mathematician named Grigory Perelman posted a series of papers to an internet preprint server that proved the conjecture. His proof was indirect and revolutionary, using techniques from physics, specifically from the way heat spreads through materials, applied to geometric shapes. The mathematical community, after several years of careful checking, confirmed the proof was correct. Perelman was awarded the Fields Medal, the highest honor in mathematics. He declined it. He was offered the Clay Millennium Prize money, $1 million. He declined that too. He reportedly lives quietly in St. Petersburg with his mother. Which takes us to fact 71. The 7 Millennium Prize problems announced by the Clay Mathematics Institute in the year 2000 are considered the hardest open problems in mathematics. $1 million for each one. As of today, only one has been solved. The Poincare conjecture by Perelman, who didn't take the money. The remaining 6 are the Riemann hypothesis, which we've already visited, P versus NP, the most important open question in computer science, the Navier-Stokes equations about fluid dynamics and whether smooth solutions always exist, the Hodge conjecture about algebraic geometry, the Burge and Swinnerton-Dyer conjecture about elliptic curves and number theory, and Yang-Mills existence and mass gap about quantum physics. $5 million is sitting there, uncollected, Moving on to fact 72. P versus NP is probably the Millennium problem with the most practical consequences. P is the class of problems that can be solved efficiently in polynomial time by a computer. NP is the class of problems whose solutions can be checked efficiently once you have one. The question is whether these classes are the same. If you can check a solution quickly, does that mean you can also find a solution quickly? Most computer scientists believe P is not equal to NP, that there are problems which are easy to verify but hard to solve. If they're wrong and P equals NP, then cryptography breaks down. Most internet security relies on the assumption that certain mathematical problems, like factoring very large numbers, are hard to solve, even though answers are easy to verify. If P equals NP, those problems might turn out to be solvable efficiently, and a huge amount of digital security infrastructure would need to be rebuilt from scratch. The question has been open since Stephen Cook formulated it precisely in 1971. And here's fact 73. Speaking of factoring, the reason internet encryption works is that multiplying two large prime numbers together is easy, but going backwards, starting with the product and finding the original prime factors, is very hard. Choose two prime numbers, each a few hundred digits long. Multiply them together. That takes a fraction of a second. Now, give someone the product and ask them to find the two primes. With current algorithms and current hardware, this can take longer than the age of the universe. RSA encryption, invented in 1977 by Rivest, Shamir, and Adelman, is built on this asymmetry. Your credit card transactions, your private messages, your bank login, many of them are protected by the mathematical fact that factoring is hard, and that mathematical fact has never been proved. We believe it's hard. We've never found a fast algorithm, but we haven't proved no fast algorithm exists. Next up, fact 74. Quantum computers, if built at sufficient scale and reliability, could break RSA encryption. Peter Shor's algorithm, published in 1994, showed that a quantum computer could factor large numbers in polynomial time far faster than any classical algorithm. The catch is that building quantum computers large and reliable enough to run Shor's algorithm on the numbers used in real encryption is technically extraordinarily difficult. As of now, quantum computers have factored numbers in the tens or hundreds. The numbers used in real encryption have hundreds of digits. The gap is enormous, but the possibility has prompted serious investment in post-quantum cryptography, which means encryption schemes that would remain secure even against quantum computers. The race is on to build the new cryptography before quantum hardware catches up with the old. On to fact 75. The mathematics of symmetry is called group theory, and it was largely developed by a 20-year-old Frenchman who died in a duel the night after he wrote it down. Évariste Galois was born in 1811 and was a mathematical prodigy who twice failed to get into the École Polytechnique, the top mathematical institution in France, reportedly because he was too impatient with the examiners. He was politically radical, got arrested twice, and spent time in jail. The night before a duel, he expected to lose. He wrote a long letter to a friend, summarizing his mathematical discoveries and asking the friend to share them with leading mathematicians. The next morning, he was shot in the abdomen and died the following day. He was 20 years old. The ideas in that letter, now called Galois theory, provided the framework for understanding when polynomial equations can be solved by radicals, and why equations of degree 5 and above generally cannot be. The ideas also became foundational for abstract algebra and eventually the mathematics underlying particle physics. And that gets us to fact 76. Group theory turned out to be the language in which the laws of physics are written. Symmetry in physics means that something doesn't change under some transformation. The laws of physics are the same whether you run the experiment here or in a different location. That's translational symmetry. They're the same tomorrow as today. That's time symmetry. Emmy Noether, a German mathematician whom Einstein called the most significant creative mathematical genius thus far produced, proved in 1915 that every continuous symmetry of a physical system corresponds to a conserved quantity. Translational symmetry gives you conservation of momentum. Time symmetry gives you conservation of energy. Rotational symmetry gives you conservation of angular momentum. Every conservation law in physics, the things that never change no matter what happens, is a hidden symmetry. Noether's theorem is one of the deepest and most beautiful results in mathematical physics. Now, fact 77. Noether's path to this achievement was not straightforward. She completed a doctorate in mathematics in 1907, one of the first women to do so in Germany, and then spent years working unpaid at a university because women were not allowed to hold faculty positions. She gave lectures under a male colleague's name. Eventually, she was given an unofficial position. When the Nazis came to power in 1933, she, like all Jewish professors, was dismissed. She emigrated to the United States, where she spent her remaining years at Bryn Mawr College. She died in 1935 at 53 from complications of surgery, still doing mathematics. Which leads us to fact 78. The mathematics of fractals describes shapes that have detail at every scale, shapes that look similar to themselves no matter how far you zoom in. The word fractal was coined by Benoit Mandelbrot in 1975, but the mathematical objects themselves had been studied for some time before that. The Cantor set, the Koch snowflake, the Sierpinski triangle. These are shapes built by recursive procedures that produce infinite detail. The Koch snowflake is made by starting with an equilateral triangle, then replacing each side with a smaller equilateral triangle bump, then doing the same to each side of the resulting shape, and so on forever. The resulting shape has a finite area. You can fit it in a circle, but an infinitely long perimeter. If you try to measure its boundary in smaller and smaller units, the measured length would keep growing without limit. The coast of Britain has this property, roughly. Measure it with a 100-kilometer ruler and you get one number. Measure it with a kilometer ruler and you get a bigger number, because you're following more of the bays and inlets. Measure with a meter ruler and you get bigger still. The coastline length depends on your measuring stick, which is a strange property for a real physical boundary to have. And next, fact 79. Mandelbrot himself had an extraordinary life story. Born in Warsaw in 1924, he and his family fled to France before the war. During the Nazi occupation, he and his brother moved from safe house to safe house under false identities. At one point, he was posing as a student at a boarding school in Lyon, attending a math class he shouldn't have been able to follow. He realized there that he could translate algebraic problems into geometric ones, that he could see the shapes of equations, and suddenly the class was easy. That ability to translate between algebra and geometry, honed in hiding from the Nazis, became the foundation of his life's work. The Mandelbrot set, the most famous fractal, the one that produces the endlessly complex swirling boundary when you plot it on the complex plane, is a direct descendant of that insight. All right, fact 80. The butterfly effect is a popular name for a mathematical property called sensitive dependence on initial conditions. The name comes from a talk Edward Lorenz gave in 1972. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Lorenz had discovered the phenomenon in the early 1960s when he was running weather simulations. He wanted to re-examine a simulation and, instead of starting from the beginning, he started from the middle with numbers that were printed to 3 decimal places. The full computer had 6 decimal places. The difference, the tiny rounding, produced a completely different weather forecast. The idea was already present in mathematics. Henri Poincare had noticed similar sensitivity in celestial mechanics in the late 19th century, but Lorenz's discovery in a practical simulation context launched the modern study of chaos theory. Chaos doesn't mean random. It means deterministic but unpredictable in practice, because tiny differences in starting conditions grow exponentially over time. The weather is chaotic. So is the long-term behavior of the solar system. So are many biological systems. Moving on to fact 81. The mathematics of networks, graph theory, which we already met back with Euler and the bridges of Königsberg, has in the past few decades become essential to understanding social structures. The 6 degrees of separation idea, popularized in a play and then a film, claims that any two people in the world are connected by at most 6 steps of acquaintance. The mathematical concept underlying this is the small world property. Large networks where most nodes are not directly connected to each other, but where any two nodes can be reached from each other in a small number of steps. The internet has a small world structure, so does the collaboration network of academics. So, apparently, does the network of human acquaintanceship. The small world property emerges from a specific way that networks tend to grow. New nodes preferentially connect to nodes that already have many connections, which is the rich get richer model. This produces networks with a small number of very highly connected hubs and a large number of nodes with few connections, and those hubs keep the average path length short. And here's fact 82, a gentle one. The word 40 is the only number spelled with its letters in alphabetical order. F-O-R-T-Y. F comes before O, O before R, R before T, T before Y. Every letter in strict alphabetical order. No other number in English has this property. 1 has O, N, E, not alphabetical. 8 has E, I, G, H, T, also not. 40 is alone. This is completely useless mathematical trivia with no consequence for anything. But it's in the book, as Erdos would say, because it's delightful. Next up, fact 83. From 0 to 1000, there is only one number that contains the letter A in its English spelling. 1000. 1, no A. 2, no A. All the way up through the hundreds, no A. Then 1000, which has an A in 1000. The letter A appears for the first time at the number that represents 10 to the power of 3. If you find this relaxing rather than annoying, you're in the right headspace for this video. And that leads us to fact 84. Every odd number in English contains the letter E. 1, 3, 5, 7, 9, 11, 13, 15. Every single one has an E. This is not a coincidence that extends forever. 101 has no E, for example. But in the single digits and teens, every odd number has 1. On to fact 85. The sum of all natural numbers, 1 plus 2 plus 3 plus 4 plus 5, going on forever, is, in a certain very specific mathematical framework, equal to -1/12. This sounds insane. Adding positive numbers and getting a negative fraction? The framework involves the Riemann zeta function, evaluated at -1. In that context, through a process called analytic continuation, the value of the sum can be assigned to be -1/12 in a way that is mathematically consistent and, remarkably, physically useful. This result shows up in certain calculations in string theory and quantum electrodynamics. This doesn't mean that if you literally added up 1 plus 2 plus 3 forever, you'd arrive at -1/12. You'd get infinity. But mathematics has several ways of assigning values to divergent series, and in one of those ways, -1/12 is the natural assignment. Which brings us to fact 86. The number 1 is not considered a prime number, even though it's divisible only by itself. This is a choice, not a discovery. Historically, mathematicians sometimes did include 1 in the primes, but including it creates problems. The fundamental theorem of arithmetic, which says every number greater than 1 has a unique factorization into primes, breaks down if 1 is prime, because then you can always multiply any factorization by 1 as many times as you like and get different factorizations. Excluding 1 from the primes is a convention adopted to keep the theorem clean and useful. Mathematics occasionally makes these definitional choices for the sake of tidiness. Now, fact 87. There is a number system called the surreal numbers that contains the ordinary real numbers, the integers, the rationals, the irrationals, and also infinitely large and infinitely small numbers. John Horton Conway, the mathematician who also invented the game of life, cellular automaton, invented the surreal numbers in the 1970s. They arise naturally from a game theoretic construction and turn out to include all the ordinary numbers as well as an extraordinary menagerie of others. In the surreal numbers, infinity is a perfectly ordinary number. The number that is infinitely small but greater than 0 exists. You can do arithmetic with them. They satisfy the field axioms, the basic rules of arithmetic, and they form the largest possible ordered field. Conway was one of the most playful and inventive mathematicians of the 20th century. He died in 2020 from COVID-19 at 82. And next we have fact 88. The game of life mentioned just now is not really a game at all. It's a cellular automaton, a grid of cells, each either alive or dead, that evolves according to simple rules. A live cell with 2 or 3 live neighbors survives. A live cell with fewer than 2 or more than 3 neighbors dies. A dead cell with exactly 3 live neighbors becomes alive. Those 3 rules, applied repeatedly to a simple starting pattern, can produce structures of extraordinary complexity. There are patterns that move across the grid called gliders. There are patterns that produce an endless stream of gliders called glider guns. There are patterns that grow forever. There are patterns that simulate a Turing machine, meaning the game of life is capable in principle of any computation. Conway designed this on a Go board in the late 1960s, trying to find the simplest rules that would produce interesting, unpredictable behavior. He found them. Moving right along. Fact 89. Mathematical models of population dynamics produce a surprising and important result. Simple systems can generate chaotic behavior. The logistic map, which models population growth with a limited carrying capacity, is a simple equation. The population next year equals a constant times the current population times 1 minus the current population. That's it. One equation, one constant. When the constant is small, the population settles to a steady value. Increase the constants a bit. The population cycles between 2 values, then 4 values, then 8 values. Increase it further. Chaos. The population jumps unpredictably with no pattern. The transition from order to chaos, as the parameter increases, happens at specific values that were discovered by the physicist Mitchell Feigenbaum in 1975. The ratio of successive parameter values at which new cycles appear converges to a number, approximately 4.6692, now called the Feigenbaum constant. The remarkable thing is that this same constant shows up in virtually every system that undergoes this same kind of transition from order to chaos, regardless of the specific equations involved. It's a universal constant of chaotic transitions. And here's fact 90. The Monty Hall problem is a probability puzzle that regularly causes intense arguments. You're on a game show, 3 doors, behind one, a car. Behind the other 2, goats. You pick a door. The host, who knows what's behind each door, opens one of the other doors, revealing a goat. Then the host asks, "Do you want to switch to the remaining unopened door?" Switching wins the car 2/3 of the time. Staying wins only 1/3 of the time. This result seems wrong to most people when they first hear it. When the problem was posed in a popular magazine column in 1990, thousands of readers wrote in, insisting the columnist was wrong. Some of them were mathematics professors. The problem required exhaustive explanation and computer simulation before many people accepted it. The key intuition: when you first picked, you had a 1/3 chance of being right. The host's action doesn't change the probability attached to your original pick. It's still 1/3. But the remaining door now has all of the probability that wasn't in your pick, which is 2/3. Next up, fact 91. There's a theorem called the hairy ball theorem, and it has a perfectly sensible mathematical statement. The theorem says you cannot comb a hairy ball flat without creating at least one tuft. More precisely, there is no continuous, non-vanishing tangent vector field on a sphere. You cannot assign a smooth, non-zero direction to every point on a sphere simultaneously. One consequence: at every moment, there is at least one point on Earth's surface where the wind is not blowing horizontally, where the wind velocity is exactly 0 or perfectly vertical. The theorem guarantees this point must exist. It says nothing about where. Henri Poincare stated the theorem around 1885. It was proved by Brewer in 1912. Which leads us to fact 92. Brouwer, who proved the hairy ball theorem, also proved the Brouwer fixed point theorem, which says that any continuous function from a disk to itself has at least one fixed point. A fixed point is a point that the function maps to itself, a point that doesn't move. One physical interpretation: stir a cup of coffee. No matter how you stir, there will always be at least one point in the coffee that ends up exactly where it started. Another: take a map of a country and place it on the ground somewhere inside that country. At least one point on the map is directly above the corresponding point in the real landscape. These are not tricks or approximations. They're guaranteed by pure topology. Alright, fact 93. The traveling salesman problem is one of the most practically important unsolved problems in optimization. The setup: a salesman needs to visit a list of cities and return home. What's the shortest route for a small number of cities? You can check every possible route. For a large number, say 100 cities, the number of possible routes is so large that checking them all would take longer than the age of the universe, even with the fastest computers. The traveling salesman problem is NP hard, meaning if you could solve it efficiently, you could solve any problem in NP efficiently. It's one of the landmark problems in the P versus NP question. In practice, there are very good approximation algorithms that find routes close to optimal, and these are used extensively in logistics, shipping, circuit board design, and genome sequencing. But finding the guaranteed shortest route in general remains computationally intractable. And that gets us to fact 94. There are only 5 convex regular polyhedra, which are 3-dimensional shapes, where every face is the same regular polygon, every vertex looks the same, and the shape is convex. The tetrahedron: 4 equilateral triangular faces. The cube: 6 square faces. The octahedron: 8 equilateral triangular faces. The dodecahedron: 12 pentagonal faces. The icosahedron: 20 equilateral triangular faces. These are the Platonic solids, and they've been studied since ancient Greece. The Pythagoreans knew about them. Plato, in his dialogue Timaeus, associated each solid with one of the classical elements: the tetrahedron with fire, the cube with earth, the octahedron with air, the icosahedron with water, and the dodecahedron with the cosmos. Euclid proved there are exactly 5, no more and no fewer. The proof appears in the last book of the Elements, suggesting Euclid may have been building toward it all along. On to fact 95. The mathematician John von Neumann, who made foundational contributions to quantum mechanics, economics, computer science, and mathematics itself, could memorize phone books. Colleagues described him as able to recall lengthy passages verbatim after reading them once, to perform complex calculations faster than mechanical calculators, and to give detailed technical lectures on subjects he'd encountered only briefly before. He spoke 6 languages. Von Neumann helped design the architecture of the modern computer, the von Neumann architecture, where instructions and data are stored in the same memory, while simultaneously working on the foundations of game theory, quantum logic, and the Manhattan Project. He believed later in life that the human brain's processing was qualitatively similar to the operations of computers, and he was working on a book comparing the brain to digital computation when he died in 1957. The unfinished manuscript was published posthumously as The Computer and the Brain. Moving on, fact 96. Game theory, the mathematical study of strategic decision-making, started for all practical purposes with a 1944 book by von Neumann and Oskar Morgenstern. The central example is the prisoner's dilemma. Two people are arrested and held separately. Each can cooperate, meaning stay silent, or defect, meaning betray the other. If both cooperate, both get a light sentence. If both defect, both get a heavy sentence. If one defects and the other cooperates, the defector goes free and the cooperator gets the heaviest sentence. If you analyze this purely from self-interest, both players should defect, regardless of what the other does. Defecting is the better choice for you individually. But if both defect, they end up worse than if both had cooperated. This tension between individual rationality and collective outcome is at the heart of enormous swaths of economics, political science, evolutionary biology, and international relations. Arms races, climate negotiations, free rider problems, tragedy of the commons, all of these are, at some level, prisoners' dilemmas. John Nash, the mathematician portrayed in the film A Beautiful Mind, extended this work by proving that every finite game has at least one equilibrium, a set of strategies from which no player has an incentive to unilaterally deviate. This is the Nash equilibrium. And here's fact 97. The universe appears to be mathematical in a deep sense. This is not a new observation. Galileo wrote in 1623 that the book of nature is written in the language of mathematics, and that without understanding that language, you wander about in a dark labyrinth. The strangeness is this: why should abstract mathematics, invented by human minds, working in isolation, often for purely aesthetic reasons, describe the physical world so well? The physicist Eugene Wigner wrote about this in 1960 in an essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Mathematics developed for its own internal reasons, following beauty and logic, turns out to be precisely what physicists need to describe reality. Group theory, developed in the 19th century for purely abstract reasons by Galois and others, turned out to be the exact language of quantum mechanics and particle physics decades later. Riemannian geometry, developed in the 1850s as a mathematical curiosity about curved surfaces, turned out to be the exact geometry of space-time as Einstein needed it. This keeps happening. The tools mathematicians build for fun turn out to be the tools the universe is built from. Nobody fully understands why. Next up, fact 98. One current theory, the mathematical universe hypothesis, associated with the physicist Max Tegmark, proposes that the universe isn't merely described by mathematics, but actually is mathematics. In this view, mathematical structures don't just correspond to physical reality, they are physical reality. Every mathematical structure that exists physically. Our universe is one structure among infinitely many. The reason mathematics is so effective at describing the universe is that there is nothing else, no physical stuff that mathematics is approximating. It's mathematics all the way down. This is not mainstream physics. It's a philosophical hypothesis, but it's held seriously by some serious people, and it has a certain austere elegance. If mathematics is all there is, then the unreasonable effectiveness of math disappears as a mystery. Of course, math describes the universe. The universe is math. Which brings us to fact 99. Mathematics is not finished. This might seem obvious, but it's worth sitting with for a moment. Every year, mathematicians prove new theorems, some small and incremental, some genuinely surprising. New connections between fields appear. New structures are discovered. New tools are developed. In 2019, mathematicians proved a result in combinatorics that required building an entirely new framework to state the problem and another to solve it. In 2023, a high school student found a proof of the Pythagorean theorem using trigonometry, something mathematicians had believed was impossible because the usual proofs of trigonometry depend on the Pythagorean theorem creating a circle. She found a way around the circle. The questions don't run out. The Riemann hypothesis has been open since 1859. The Collatz conjecture has been open since 1937. P versus NP since 1971. The twin prime conjecture, whether there are infinitely many pairs of primes separated by exactly 2, has been open since at least the 18th century. Some progress was made in 2013 when Yitang Zhang proved there are infinitely many pairs of primes separated by at most 70 million, and subsequent work has reduced that gap, but the final answer remains out of reach. And that leads into fact 100. The future of mathematics will probably involve computers more deeply than it does today. Proof assistants, computer programs that can verify mathematical proofs line by line, have already been used to verify some famous and complex proofs. The four-color theorem which says you need at most 4 colors to color any map so that no 2 adjacent regions share a color, was proved in 1976 with extensive computer assistance that checked cases too numerous to verify by hand. This was controversial at the time. Is a proof that requires a computer to check actually a proof that humans can understand? More recently, AI systems have been helping mathematicians explore new ideas, suggesting patterns that humans then pursue. The collaboration between human mathematical intuition and machine computational power is still early, but it's already producing results. Some mathematicians believe the next generation of AI will prove major open problems within decades. Others are more skeptical, noting that the hardest problems aren't just hard because the computations are large. They are hard because nobody knows what approach would even work. A key insight can come from anywhere, from a dream, from an embarrassing doodle in a lecture, from a conversation between a refugee posing as a student in occupied France. And finally, fact 101. 43,000 years ago, someone sat down with a baboon bone and a sharp stone, and they made marks. We don't know their name. We don't know what they were counting, days, moons, something else entirely. We don't know if they knew what they were starting. They probably didn't. But they were doing what we've been talking about this whole time, taking the messy, continuous, overwhelming flood of the world and organizing it into something countable, something holdable, something that could be written down and passed to another person who could carry it forward. That impulse to count, to measure, to find a pattern is what produced the tally marks on the wolf bone in Czechoslovakia, and the clay tablets in Mesopotamia, and the papyrus rolls in Alexandria, and the notebooks of Euler, and the attic work of Andrew Wiles, and the preprint papers of Grigori Perelman, and every equation that every student has ever scrawled at every kitchen table in every country in the world. The entire history of mathematics is a single line of thought passed hand to hand across 43,000 years, getting longer and stranger and more beautiful with every generation. And it's still going.